Uh, Hello, this is the synopsis of chapter 5. Before reviewing the synopsis or starting to study for the chapter 5 material, go into Moodle and go over the calculator. I have a calculator help file in there that tells you about the settings that you need to have on your calculator. That's in Word. And then there's also a PDF of a calculator tutorial. That's a really easy tutorial to follow that the publisher of this book has issued that shows you step by step how to do these steps on the calculator to do the same types of calculations that you'll be doing in this chapter. So make sure you look at those two things and then come back to this video. Okay, so we're going to be looking at the time value of money, and it's basically going to show you how money over time is worth more than the money today. And it's going to show you the power of compounding. That's basically the essence of the time value of money chapter, is how money grows over time at certain rates of return and the power of compounding. All right, so let's take a look at what we're going to be looking at. So this is what we're going to be talking about in this chapter: the future value of a lump sum, which is if you make it a lump sum investment today, how much is it worth in the future? The present value of a lump sum, if I want to have a certain amount in the future, how much do I have to put in today? Okay. And we're also going to look at how we can find out how many years it would take us to get to a certain amount, or at what interest rate we would need to get to a certain amount. We're going to look at annuities. Those are equal payments, either in other words, how much money would I have to put up today if I want to be able to withdraw an equal payment? Or if I want to save in equal payments, how much money do I have at the end? So those are annuities. And then we're going to look at various rates of return, and finally an amortization schedule. So what a lot of people in finance do is they use this timeline to tell you how much, to kind of just lay out the problem, if you will. So this basically what the timeline shows is that 0 is today, and then you have these various periods. It can be months or years. This would be your present value here. This is your future value. And then you have these various cash flows or payments. This is where the interest rate goes, or the rate of return. All right, this is a timeline just simply showing a lump sum in 2 years at a certain rate of return. And this is a timeline showing an annuity over 3 years, either putting in $100 or taking out $100 over 3 years. We're not going to cover uneven cash flow streams in this chapter because I cover that in a later chapter, chapter 9. So you can skip the uneven cash flow stream for this chapter. But basically all they're saying here is that where an annuity is an equal payment, an uneven cash flow stream is different payments. So this would be an investment where you put up $50 and then your cash flows, this is what you're getting back in year 1, 2, and 3. Okay, so let's look at this first problem. It's the future value of $100 in 3 years at 4%. So you can do this the long way, and you could take, well, what would $100 be worth at 4% at the end of year 1? Well, if you took $100 times 1.04, that would give you $104. And you can keep calculating the balance here by 1.04, and you would get your future value. But an easier way to do this is to use the future value formula. So here they're showing you this long incremental way, but this is the formula for the future value. The future value equals the present value times 1 plus the interest rate to the nth power. So, and you can use this formula if you want, or you can use your financial calculator. And it's this, and they also show you in the book how to step by step how to do this in Excel. Okay, but this is the formula for the future value. It's simply 1 plus the interest rate to the nth power. That's the number of periods. times the present value. That gives you your future value. So let's look and see how you would put that in your calculator. Well, on the third row of your keys on your financial calculator, you're going to see these keys. These are the inputs. So we're going to put in 3. It doesn't matter which formula you use, or which doesn't matter what order rather you use. And the first thing you want to do on your calculator is clear it. So hit second and then clear work, the second button and then clear work. That's at the lower. You hit second up here and then clear work down here. Right. So you're going to put in 3 for N. That's 3 years. 4 is the interest rate. Payment is 0 payment. 100, the plus minus sign, and then the present value. You put in a negative 100 because you're investing that money, and that makes this number come out positive. If you put this in as a regular, as $100, this number is going to come out negative. That's fine. That's okay too. You just disregard the negative sign. But it's better to do it the right way. Anytime you have a cash outflow, you're investing money, that should be negative. So you enter this all in, you hit compute and future value. Compute being the upper left side here. And that will give you your output of 112.49. Okay, so that's the future value of a lump sum. Next, we're going to talk about the present value of a lump sum. So what they're saying here is, how much would I have to save today if I wanted to have $100 in 3 years and I could earn 4%? So let's see. Here's the formula. The future value divided by 1 plus the interest rate to the nth power is going to give us our present value of 88.90. So it's going to be 1.0. So it's $100 divided by 1.04 to the third. That's 88.90. So if I put 88.90 in an account today, I would have $100 in 3 years. So here's your inputs, and then you just hit compute and the present value, and that gives you your output, which is the answer. Now you can also solve for other things. You can solve for I, for example. Now, if you looked at the future value or the present value formula, you'd have to use algebra to solve for the interest rate, but we can just put it in our calculator here. And so we're going to put in all of these inputs, hit compute and I-Y, and we get 6%. Now, you have to make sure to put the present value in as a negative number, or you're going to get an error message, because the calculator reads, if you have a situation where you have to enter in the future value and the present value, one of them's got to be a negative. It should be the present value, or you'll get an error message. So make sure you enter that present value in as a negative number. Okay, here we're solving for N, and it's asking how long, if sales would grow at 10% per year, how long before sales would double? So they're just asking how long to double your money. So you can pick any number here as long as it's double for your present value and your future value, and you can hit compute N, and that will give you so in 7.3 years at 10%, you would double your money. You can also, other problems that would solve for N might just say, if I invested $1,000 and at 10%, I want that to grow to $10,000, how long would that take? So I could put in 1,000 and 10,000 here and see how long that would take. But this just happens to be a double your money problem, but it can be any type of duration to solve for N, or any type of amount here to see how long it takes you to get to a point from a present value number to a future value number. Okay, and then down here in the notes, whoops, just lost, hang on, let me go back. So this is showing you, there's this really cool trick called the rule of 72. The rule of 72 tells us how long to double our money. And so all you simply do is put, this is just a math trick. You put 72 as the numerator. So look, if we take 72 divided by 10, we get 7.2 years. Look how close that is to the actual answer there. And so I wrote in some other examples here. What if you could earn 12%, which is that's actually the average return in the market historically for the last 90 years is 12% in the stock market. So you could take 72 divided by 12 equals 6 years. So if you could make 12%, it would take you 6 years to double your money. If you could make 8%, which is a more conservative estimate, you double your money in 9 years. If you just were being real conservative and put your money in government bonds and was only making 3%, it would take you 24 years to double your money. So this kind of illustrates why you really need to be in the stock market to invest, to grow your wealth over the long run, be in a diversified portfolio in the market. All right, next we're going to talk about annuities. An annuity is an equal payment. An ordinary annuity, or if the problem just says annuity, that's an ordinary annuity. If they don't say ordinary, but they just say annuity, it means it's an ordinary annuity, which means payments are made or received at the end of the period, at the end of the year or the end of the period. An annuity due is when payments are made or received at the beginning of the period. So if I was saving and it was an annuity due, I would be saving at the beginning of each year, putting money in at the beginning of each year. Or if I'm taking money out, it would be at the beginning of each year. So they don't, so for this, for the annuities, I'm showing you how to use the financial calculator to do it, but go back in the book and look at the formula just so you understand what's going on with the formula, that you're not just pressing buttons in a black box of the calculator and not really understanding what's happening. So what we're doing with an annuity is here, we're calculating the future value of this annuity. And so it's basically what this is saying is if I put $100 in an account at the end of each year for 3 years at 4%, what is it worth at the end of 3 years? How much money do I have? And so we put in, these are the inputs, and then you compute future value. So you'll notice present value 0 because there's no lump sum, but the payment is $100. And so we end up with a future value of $312.16. The next slide, what's the present value of an annuity? What this is asking is, if I want to be able to take out $100 a year for 3 years, how much do I have to put up today? And so again, you put the inputs in. If we put $277.51 in an account, and that's earning 4% over 3 years, I would be able to withdraw $100 a year at the end of each year. And then at the end of the 3 years, it'd be worth 0. An annuity due is when the payments, as I said, payments are made or received at the beginning of the period. So if you look at the formula for the future value of an annuity due, you're just taking the same formula of an ordinary annuity, but they're tacking on 1 plus the interest rate at the end of it. So you could actually take this answer here, the answer you could take, wait a second, you could take this answer, multiply that by 1.04, and that would give you the answer to the future value of an annuity due. Because basically what you're doing is, instead of putting the $100 in at the end of each year, you're putting it in at the beginning of each year. So you have one extra period of compounding. So let's go back to the annuity due future value. Now you have to set your calculator to begin mode. They'll show you that in the tutorial. Let me just show you real quick though. What you're going to do is you're going to hit second, and let's clear that first. You're going to hit second, and then above the payment is begin, second and begin, and then second and set, the enter key. And it's going to say begin. And when you see the zeros on your calculator, you're going to see it says begin at the top. You're in begin mode. Then you can solve this problem. As soon as you finish that, set it back to end, second, and begin, and then second and set, and you're back. Okay, so you set your calculator to this begin mode and then put these inputs in, hit compute future value, and you see that it's that's your future value of an annuity due. And it would be the same as taking this 312.16 times 1.04 if you were using the formula. All right, and then same thing with the present value. We could take the 277.51 and multiply that by 1.04, and we would get the present value of an annuity due. So this is if I start to say, how much would I have to put in today? It's kind of counterintuitive. It's saying, how much would I have to put in today if I wanted to make an immediate withdrawal of $100, and then at the beginning of year 2, beginning of year 3. And so that answer is 288.61. Okay, and then this is just another annuity calculation. This would be $100. What's the present value of a $100 ordinary annuity at 4% over 5 years? So if I wanted to be able to withdraw $100 for 5 years, how much would I have to put up today? And that's 445.18. Okay, so we've gone over the present value of a lump sum, future value of a lump sum, present value of an annuity, and a future value of an annuity. Okay, this just shows over time, annuities over time. A 10-year annuity, if you wanted to withdraw $100 for 10 years, it would be $811 that you'd have to put up. If you wanted to be able to withdraw $100 for 25 years, it would be $1,562 that you'd have to put up. What if you wanted to withdraw $100 forever? Well, that's actually called a perpetuity. And the formula for a perpetuity is the payment divided by the interest rate. $100 divided by 0.04 equals $2,500. So if I had $2,500 in an account, think about it. What's $2,500 times 0.04? $100. So if I had $2,500 in an account and I was earning 4% interest, I could take $100 out a year and never touch the principal. So that's essentially what a perpetuity is. All right, this is a really interesting example because it really shows the power of compounding. So let's look at this example here. A 20-year-old student wants to save $5 a day. She places $5 in the drawer. At the end of the year, she has $1,825. How much will she have when she's 65 years old? At 8%. Okay, so this person is going to save at the end of every year $1,825, $5 a day. That's $148 a month, just to put it in perspective. Gets 8%, saves until she's 65, so 45 years. She has $705,000 at the end of this. So this is a really interesting example because it shows, for example, when you do this problem, just change this number to 50. Because think about it, if she's 65, she may not need to withdraw this money. She might say, hey, I'm going to let it ride for 5 more years. This number will be well over $1 million just at 5 more years. So you can really see the power of compounding here. Then also, if you change this interest rate a little bit, if this were 10%, it would be over $1 million. So take a look at this and play around with these numbers. It's really interesting. Okay, now let's look at the next stage of this example. What if you didn't start saving until you were 40? So you procrastinated for the last 20 years, and then you only have 25 years to save until you're 65. And instead of having 705,000, you only would have 133,000. So you can see why it's really, again, the power of compounding is huge. It's really important to start saving as soon as you can, and you just save methodically over the long run. That's the way to wealth. Okay, now let's look at this final example. This is where the 40-year-old, what if you waited till you were 40, but you still want to have that 705,000 when you're 65, as if you started saving when you're 20? How much would you have to save? Okay, so here we've got the 40-year-old saving for 25 years. They want to have 705,000 at the end of this when they're 65. How much do they have to save a year? It goes from 1,825 a year to 6,000 to 9,648 a year, which is not doable for most people. So if you think about it, if you divide the 1,825, that's 104, that's $148 a month. So 150 a month, 150 a month, most people can do that. But if you were advising this 40-year-old and said, hey, you've got to save 96.48 divided by 12, $804 a month you'd have to save. Most people are not going to be able to do that. So this really illustrates the power of compounding, why it makes sense to start saving as soon as you can and over the long run. All right, we're not going to cover the uneven cash flows in this chapter, so let me skip that. And okay, in this here we're covering interest rate classifications. So if something is stated, if something pays an annual rate of interest, that's called the nominal rate. That's the stated rate or the annual rate. The periodic rate is if they pay interest monthly or quarterly or semi-annually. And so if interest is paid more often than annually, then we have what's called the effective rate, which is more than the nominal rate. Okay, so let me show you this formula. So if you, for example, if you were earning 4% interest semi-annually, you're not really making 4%. You're making more than 4% because 4% paid semi-annually is 2% every 6 months. And so you're making interest off of that interest. And in other words, in the first 6 months, you got 2% interest. So in the next 6 months, you're getting 2% more off of that larger balance. So because of compounding, you're actually making more than 4%. So because of compounding, if interest is paid more often than once a year, you're making more than the annual rate or the normal rate. So you can use this formula and it's called the effective annual rate. So you can use this formula. If you are making 4% semi-annually, you're actually making 4.04%. Here's how you figure it out. It's 1 plus the nominal rate divided by the number of compounding periods to the power of the number of compounding periods minus 1. So 1 plus 0.04 divided by 2 squared minus 1 equals 4.04. If we were calculating, if it were paid quarterly, we would divide by 4 and take it to the 4th power. And monthly would be divided by 12 into the 12th power. And so anyway, that's called the effective annual rate. And they're just showing you here, they did all these calculations. And this is what you would be making if you were getting 4% semi-annually, quarterly, monthly, actually daily. Some bank accounts pay interest daily. You would divide by 365 and take it to the power of 365. But you see, it doesn't really make that much of a difference on the overall annual rate. So if you are calculating, doing some calculations here, this is the way I normally, there's 2 ways to do the calculations for future value or present value when you have more frequent compounding than annually. So let's look at this. What is the future value of a 3-year annuity if it pays 4% compounded semi-annually? So for N, you're going to take the number of years and multiply it by the number of compounding periods. So N is now going to be 3 times 2 is 6, okay? And the interest rate is going to be divided by the number of compounding periods. So the interest rate is going to be 4 divided by 2, which is 2. All right, so in your calculator or in the formula, you're going to put in 2% is the interest rate and 6% is the number of periods. And another way to do it, I don't really do it that way. I would make this 2 and I would make this 6. But another way to do it is to use that effective annual rate formula and calculate the effective annual rate and then use that as your interest rate. That's what they're showing you here. All right, and then the last thing for the chapter is loan amortization. So if you have a loan, the first thing that you want to do is figure out what the annual payments are, what the payments are. So this is a really easy example. We have $1,000 loan that pays 4% in 3 equal payments. So think about 4% a year. It's a 3-year loan. They're going to make one payment a year at 4%. It's $1,000. And so the first thing you do is calculate the payments. So you just put in the $1,000 is the present value. That's what you're getting. It's worth, when the loan's paid off, it's zero. The balance is zero. So the future value is zero. Put in your interest rate and N, and you calculate the payment. And so the payment is $360.35. Okay, so let me go to this, skip to this, because this shows you all the math in those prior slides. All right, so if we have our beginning balance, this is the amortization table. Our beginning balance is $1,000. We know we're going to make 3 equal payments now of $360. So in order to calculate the interest, you take the beginning balance times the interest rate. So $1,000 times 4% is $40. So out of this first payment, $40 of it's going to be interest and $320 is principal. Subtract out the principal, 1,000 minus 320, and we have 680. That becomes our beginning balance in year 2. So you take 680 times 4% and you get $27 and so forth. And then you just do this again. So what this is illustrating to you is that the interest is higher at the beginning of the loan, and as the loan progresses, you're paying less interest and more principal. So the lesson here is that if you make extra principal payments at the beginning of your loan, you can really reduce the interest, because it reduces your principal balance from which the interest is calculated. So if you have a home mortgage or a car loan and you want to pay it off early, making extra payments, additional principal payments at the beginning of the loan, at the beginning of the life of the loan, can really save you a lot of interest. But if you have a car loan, say a 6-year car loan, and you only have 2 years left on it, you've already paid most of the interest. It really wouldn't behoove you to pay it off early. So this is just illustrating how as the life of the loan progresses, you're paying less interest and more principal. Okay, so that is the end of chapter 5. So the way I would study for chapter 5, as I mentioned, look at the tutorials for the calculator first, go over this PowerPoint synopsis, and then go to the book, take a look at the formulas, and do some of the, do the suggested homework problems. And hopefully this will help you this will help you in going through the chapter, because this chapter can be kind of complicated. Also, if you're interested in learning more about saving, how to make your money grow over time, I will always recommend to my students to open up a Roth IRA. And if you want more details on how to open up a Roth IRA and try to save systematically over time, and what to invest in. I mean, I don't make recommendation investments, but I can basically tell you, it's better to be in the market than just to be in a savings account or in CDs or in government bonds. And so if you want to talk in more detail about investing, since this is, this chapter is very important chapter, I think this is the most important chapter in the course, because it teaches you how you can become financially independent by saving over time. Send me a text or an email, and we can call and chat, and I can give you some additional information. Okay, take care, everybody. Bye.